So in this problem, we're trying to essentially write a function that returns true if there exists a path from the root to the leaf that contains at least n instances of a certain element in the tree. So along that path, you have to find at least n instances. So once again, this is a tree problem, and one of the best ways to solve tree problems is using recursion, specifically thinking about recursion in list comprehension, given that we don't have a whole lot of lines to work with. So in this problem, we want to see whether at the certain point that we're at, whether there is a viable path from this point to the leaf. So if we're thinking of an example tree, one way we could think about it is there some sort of path that contains the necessary number of elements? But in addition, we could think about it as, let's say in our case, if n was equal to 2. Then along this path on the left-hand side, we look for 2 instances of the elem. But we could also view this from this perspective, because this is also a tree, meaning recursively things work the same. And in this case, we could look at it and say, oh, does this path have n equals maybe 2 or n equals 1 instances of the elem, depending on whether or not this was an instance of elem, right? So if the top node was an element, then we'd only need to find n equals 1 instances of elem along this path right here. However, if the top root node was not an element, then we need to find 2 along this path. So that basically sets up the frame and structure for our recursive call. Notice here that they provide one of the base cases where they say, oh, well, n is 0, and that's trivially true. So let's deal with our recursive cases where we are recursing through our tree and we need to evaluate whether something works. So our 2 recursive cases are right here. I know they're right there just because of I know this problem, but you can realize that they're right there because you realize that we are missing one base case that we need to account for, and this is normally the base case for every single recursive tree problem. So our 2 recursive cases are right here. And in one case, we need to consider where the node we are working at actually has the label elem. So we can say has elem. And the other case is where we do not have elem. So in the case where we have elem, or we can say, so t.label equals element, or elem, then what do we need to do? Well, we know we need to recurse, since this is a tree problem. And when we recurse, what we'll essentially be doing is we'll be getting an answer for every single one of our branches. So let's say I have 10 branches, then I'm going to be getting 10 answers. And these 10 answers are all Booleans according to the problem, because in this problem it says it returns true or false. So essentially we're going to have 10 different answers of either a true or a false. So if we know, once again looking at like the structure, right? If we look at all of our different branches and we assign arbitrary values, like one branch returns a true, the other branch returns a false, other branch returns a true, etc. Let's assign arbitrary values and understand what are we looking for. So if we see that our several branches some return true and some return false, what do we care about? Well, we care about the fact that there's at least one true amongst all the answers. Because this whole question is, does there exist a path? Now, sure, for 9 out of the 10 branches, the answer might be a false, and we ignore those branches. But all we're looking for is one branch where the answer to the recursive call comes out as a true. And when that comes out as a true, we know that we can say true, because there exists one path from our branches, and so we can go from us to our branch and go down that one path that exists. There exists at least one path. And so as a result, all we're really looking for, if there is a true in the recursive calls of this function on all of our branches. For B and T dot branches. Now the thing is, what should be the thing inside of this parentheses? Well, we are still looking for elem. Now, since we've found one instance of elems according to this, assumption right here, we say, oh, we're only looking for n minus 1 more instances of elem. And we are calling this on the branch rather than on the tree. So our parameters are elem, n minus 1, and b. Now, in the other case, if we don't have elem in that one label, right? So we're looking at this next, at the else, and we say, oh, this node does not have an elem. We once again do the same process where we do a recursive call on each branch, and our interaction that we're looking at between branches is, does there exist at least one true? So we would once again write the same thing. With the one difference being that we don't decrement n, because we did not find one, so we still need to find n more instances. So hopefully this part makes sense, and hopefully the whole idea of finding that one true makes sense, because once again, you just make up fake results for each of the recursive calls on the branches, and think about, oh, okay, given these set of results, what do I care about? Well, I really just care if one of these is true, because as a result, I can say, yeah, at least up to my node, I have found a path that fulfills this condition. And I don't need all the paths to fulfill the condition, I just need one. So as a result, I just need to look for one true. So we've dealt with the case, we dealt with the recursive cases, and we dealt with the case where n is equal to 0. But there's one more, which is, say n was not equal to 0. At the end of the day, this is a tree, and that tree has to stop recursing at some point. That point is always the leaves. So we say, oh, okay, well, what if t becomes a leaf? Oops. So if t is a leaf, then there's two things that we care about. One case that we care about is like the amount of n that we have left, right? Because n is kind of a counter, and it keeps track of how many n's have we seen so far. So if I said that I wanted 7 n's, and at this current point when I'm at the leaf, my n is 4, that means I haven't reached my goal, because somehow I need to find 4 more n's with just a leaf. It's not possible, so I'd say false. So what is possible? Well, the only thing that's possible that can be done with a leaf is the case where we have n equal to 0 when we get to the leaf, or we have n equal to 1 and the label is lm. Right, so that leaf fulfilled the last end that we were looking for. Now n equal to 0, that is this thing right here. That's not something we have to worry about, because if n equals to 0, the base case that they already provided will return true. So we've already considered that case. That's something that's not what we're going to worry about. However, we do need to consider, if t is a leaf, then this can only be true since we don't consider n equals 0. This can only be true if n is equal to 1 and t dot label is the final lm that we were looking for. So the key thing to take away from this problem is that this really involves, once again, like the recursive leap of faith. Try to understand that it doesn't matter what comes out of the recursive calls, but let's just assume that we do recursive calls on all the branches and they come up with random answers. How should these answers interact? Well, in other problems, we'd have the answers maybe have them all added to each other. But in this case, the list of answers, all we care about is that one of these answers from the list of answers is a true. And that is what our recursive calls are in these two cases. We're just looking for the one true in that list of recursive call answers. And as a result, that is the problem.